Problem number 1 in Chapter 7 demo. One graph in the figure represents a normal distribution with the mean or center at 11, and it deviates by 2. And the other one has a mean of 16 and deviates by 2 also. Let me pop this out a little bit. So the center is the peak. So A has a peak here. If I go down, then its peak is 11, its center is 11, and B peaks here, so its center is 16. So let's look at our options. Take a minute to read which one and see if you could figure out which one is which. Maybe pause the video. And then once you're ready, put it back on to see if you were correct for your problem. Okay, so A has a center of 11, so mean of 11. So A has a mean of 11. So I see there's 2 options. And then B's mean is 16. Okay, so let me close this. And I have to see why. Because a larger mean shifts the graph to the right, so a larger center. So 16 is a larger center. Did it move it to the right side? Yes. And then this one says it would shift, a larger center would shift it to the left, which would mean B would be on the left side of A, which is not true. I'm going to minimize this just to have more space. Okay, question 2. The normal curve is provided, and then you have to know what these symbols mean. You might have them like on that handout that's on Canvas, the symbolic notation here. So the symbol here is the Greek letter mu, and it's for mean, which is the center or the average results. And I see that it's a negative 21 on mine. Some of you might have a positive number. I think that if you get a negative, excuse me, a negative 1, it's a little bit confusing for students. And then what does it deviate by? So it goes from you're adding some, you have to figure out what you're adding here. So one way to do it, if you're not too sure, is, let me see, get more help with the calculator here, is to take the number to the right, which in my case is a negative 19. I would use a scientific calculator. These are cumbersome as you're working with. And then you subtract. So this negative key is different from the subtraction. So subtract the center, the mean, which is a negative 21. And then equals. Okay, so I try that again because I made a mistake when I input it. So I say these are cumbersome. So a negative 19, subtract a negative 21, and it comes out to be 2. So they're going up by 2. So your standard deviation should not be negative. I'm going to see similar question for a positive one. Well, that didn't give me a positive one. I mean, they might all be negative. I'll just quickly put what the answer is to see if oh yeah, here's a positive one. So see how the center is 13 and it's clear that it's going up by 2. But if I do 15, subtract 13, that is 2. So it's easier to relate to when it's a positive number. So just be careful if you happen to get a negative. Oh, it marked it wrong. That shouldn't happen. If you see that happen, send me an email. It should just, if I have already done it correct once, it should keep the correct answer. Okay, so question 3. Michael went to unless I put save here, I don't know. Michael went to a driving range with his rangefinder and hit 75 golf balls with his pitching wedge and measured the distance it traveled in yards. And then here, if you click on this table, it shows all his results. Use technology. For us, it's StatCrunch. So I'm going to open this in StatCrunch. Close this. Construct a relative frequency histogram. So basically a histogram, a relative frequency is that instead of actually putting the distance on the, the frequency in terms of just a number instead of like a percentage. So let me show you when I don't do that. So graph, histogram, and then we'll select both drive and distance. And then here it's frequency, like how many times did he hit 100 yards, and how many times did he hit 99 yards and build the bars. But if we want to say like what percent of all the 75 times that he hit the ball was it 100, then that's relative frequency. So it's sometimes convenient to put value above bar as well, just to see. Sometimes it's hard to read here. Okay, so why does it have to? Relative frequency. Oh, because I didn't tell which one was the input and which one was the output. That's something new. I hadn't seen it before, but it's the second one. Now this one starts at 96 and this one starts at 93. So if you want to start it at the same place, you can do options edit, but we just want to see the general shape here. I noticed just some patterns, like these are two that are the same, and I see two that are the same here and two that are the same here. But the thing is that in this one, it's peaking like almost below 30. And I can zoom in to see, but this is like 0.30, and when this is below 25. So here I see this is at 29. So definitely then this one. I'm going to go options, edit, and I'm just going to do regular frequency. And it should be the same shape, except now here it's like 5 times he hit 100 and hover over here, 102. There was, it's usually the lower bin here, the cutoff on the lower, the cutoff on the higher end. So this one here would be actually 102. The way they graphed it is kind of interesting here. Sometimes the follow-up question is this one. Okay, then the shape. So think about what the shape is. It seems pretty bell-shaped. You might think it's slightly skewed on this left-hand side. But there's no option for slightly skewed to the left. So it's approximately normal. Uniform means like they're all the same height, and they're not definitely all the same height. And then this one just says, okay, if I did put the normal curve, which one would be the correct? This is like if the person chose that it's uniform, that all bars are the same height, which we said was not the case. No pattern means that you can't, it doesn't look bell-shaped, it doesn't look uniform, it doesn't look like one of the traditional shapes we talked about. So our choice, which would be these two, and that's just the two choices here. There's one that says 25 and the other one that says 32. So we'll choose the one that says 32. Do you think this normal density function accurately describes the distance? Yes, because it's pretty bell-shaped. Yes, because the histogram shape resembles the normal curve and the area of each bar is roughly equal to the area under the curve for the same region. Yes, because the distance Michael hits the ball is a random variable, so it's normally distributed. No, if I hit the ball, it's still a random variable, but doesn't mean mine is going to be normally distributed. Necessarily, we don't know if that would happen. We'd have to kind of do some studies to see if that would happen. So like, even though this piece is like above the bar, we can cut that piece off and cut it into smaller pieces to fill in these little gaps. And like this little slightly piece here that goes above, we can kind of fill in these, like smaller gaps here. So you roughly can fill that bell-shaped curve with this green area here. Question number 4. Suppose the monthly charges for cell phone plans are normally distributed with the center of 69. And already I can eliminate 2 choices because there's only 2 choices that have a center of 69 and a standard deviation of 15. So I have to see which one increased by 15. So 69 plus 15 is 84. So it's this one here. And then shape the region that represents the proportion of plans that charge less than $54. So first of all, I have to make sure I go with the correct diagram. So my diagram was the one that had 54, 69, 84. And there's only one choice here. They all are shading to the left of 54. On the left-hand side is being shaded. But just the way the cutoffs are being labeled are incorrect. Choose the correct choice. Okay, so in part C, it says, suppose that the area that it's taking up on that space to the left of $54 is 0.1587, which is about 15%, almost 16% if I multiply 0.15 by 100. And it would be 15.87. It's about 16%. So the probability of about 16%, or the probability is about 16% that a randomly selected phone plan in this population is less or more. Well, we were doing the case that was less. So look for those context clues. Here it says less, never said more. So for sure, I know at least which choice it is. And then the dollar amount that is cutting this off here is 54. So if you randomly select a cell phone plan, the odds that you randomly choose one of these cell phone plans from these customers, that it's gonna their bill is less than $54, there's like a 16% chance of that happening. So out of every 100 cell phone bills, about 16 will be less than $54 a month. So that area is kind of representing the odds of that happening, or the probability. Usually we talk about the probability in decimal instead of percentages, and percentages are reserved for the public since that's what they understand better. Now, if we standardize this normal curve, you can go back to the video, the lecture notes on what that means. But basically, when that previous problem that we just did, instead of putting like the 54 here, like, well, before this is the 54 here in the center, they're just kind of, where is my 69 here? I just moved the place here, 54. We say like this is the center. So we say that if you land here, you're 0 deviations away from the center. But if you're here, you're 1 deviation away from the center. So we kind of label this as 0, 1, 2, and 3. So we standardize it as how far away you are from the center in terms of these typical deviations. So you could be 1 deviation away, 2 deviations away, or 3 deviations away. So we're going to need to do this on StatCrunch because it actually requires calculus, which we're not going to do. So let's open StatCrunch, get more help. Luckily for us, we can get this information on StatCrunch. So go to the stat calculators. And we're looking at different curves here eventually, but for now, we're going to look at the normal one, the standardized one. So stat calculators normal. And this, you can see now it's standardized where there's, if you're the average, then you're 0 away from the mean. If you land here, then you're 1 of those deviations from the center. If you land here, you're 2 of those deviations and so forth. So we leave this here. If we want to know the area to the right of 1.62 standard deviations, which is around here on the right-hand side, that's the X here. So see where the X is. And we want to know to the right. So right now it's shading to the left. We want it to shade the right-hand side. And we want to move it to 1.62 standard deviations. Compute. And this here will be the probability, which is the area that space it's taken up. We want 4 decimal places. So 4 numbers behind the decimal, 1, 2, 3, 4. And then check that next one. If that next number is 5 or higher, then you have to add, bump this up by 1. So then it would be 0527 if it were. But for mine, it's good as is. And then the area to the right of a negative. So negative 0.21 is between -1 and, between 0 and -1. So maybe it's 0.5 would be here. So 0.2 is probably like right here. So now we want to move that cutoff to 2.21 deviations below the center. So like if this was a height and somebody was 5'9" for a male and they were here, maybe they're like 5'8.5". And that would place them below the average height of 5'9". So they'd be below the center. So that's why that's that negative. So let's switch this because now we want the left-hand side shaded, and make sure you put the negative sign so that you're below the center instead of above it. And then 4 decimals again. So in this part, it's the same. So oh, I put to the left. It said right again. My bad. Sorry. Should be reading carefully. Probably caught that, what I was doing that. So good eye if you caught my mistake there. Okay, so this case, this last digit 1 for me, it's going to turn to a 2 because of my next digit is a 6. So I have to bump that up. So a lot of times students have difficulty with rounding issues. So just watch out for that. Okay, I'm going to show completed, and then you could just place your video on pause so that you can finish it off, because the rest is just putting different numbers. Problem number 6. Now we want the area. Oh, wait, hold on a second. Now want the area that's between these two cutoffs. So the between one is here. See how it's shaded between two cutoffs? Here it's between one standard deviation. And remember, when you're one standard deviation, the empirical rule says that you cover about 68%. There it is. It's not exactly 68%. And then if you go up, you capture 68%, I should say. So like in heights, 68% of the male heights is between, let's see, the typical male heights are like let's say 5'9". I think it's 5'9.5" in the United States. So let's say 5'9", and they typically deviate by 3 inches. So 5'9" plus 3 inches is 6 foot even. So 68% of the population is between 6 feet of the male height population is between 6 feet and 5'9" subtract 3. That would be 5'6", so between 5'6" and 6 feet. And then if I add another 3 inches, that would be 6'3". On the high end, that would capture about 95% of the population. So 95% of all males in the United States are between 6'3" and 5'3", because if I go another 3 inches below, and then if I do 3 standard deviations, capture almost all male heights. What percent of the population? 99.7. And that's the empirical rule. And it's not exact, but it's about 99.7. So it actually extends further. It doesn't stop there, because you do have like the unusual height because of, genetic conditions that, the tallest man in the world, 8 foot, is obviously maybe 4 standard deviations away from the center. But almost 99.7 is almost all. Okay. So we're going to do these. So negative 1.63. And that's the empirical rule. And I wanted to illustrate that. Negative 1.63 to a positive 1.63. So that's like almost 1.5 standard deviations from the center. 4 decimal places again. Now mine's 68. The next one's 9, so that's going to push that to 69 at the end there. Practice that rounding. And then the area between 0 and a negative 0.47. You always have to put the smaller number first. Luckily, they naturally put it in order for us, so we don't have to worry about that. You would have to put the smaller number first. So it's a very small little strip here. If you're between 0 and a negative about 0.5 standard deviations away from the center, what percent of the population of male heights falls between those two? About 18%. So between 5'9" and maybe if this is 3 inches, then maybe like 1.5 inches. So 7.5 to 5'9", about 18% of all males are within those heights. Any human measurement, animal species, when we measure physical attributes like how tall a plant can get and so forth, they always have a normal distribution. They're not skewed. We all come pretty standard as a species, like as humans. We're mostly between 5 and, or even like 4'10" and 6'2". Most of the population is between those heights. I mean, there's not a lot of variation in terms of, we're not 20 feet tall or 80 feet tall, things like that. Okay, so then you can finish the rest off if you want to put the on pause. Question 7. Find the area under the normal code to the left of -2 plus the area to the right of +2. Now, if you just put -2 here and +2 here, it gives you the area between, but we want the area to the left of -2, which means below -2, and to the right of +2, so above. So we actually want this white area, and what this is giving us is the red area. But if we know that this is 100%, then what we can do is take this area from 1, and it's already as a decimal. So 1, which is 100%, subtract this 0.9545. And that gives me the remaining area if this is 100% in terms of the area. So put that in here. Another way you can do this is just put it back as a standard and say, okay, what's the area to the left of -2? And that's this number here, 0.0228. And then to the right of +2, it's also like we call that symmetric. So it's the same space that it's taken up. So that's a plus another 1. I'll just do ×2 to do it faster, since it was the same, but you can do add, and then you get 0.0456, just of how it was rounded. But it should, if you're off by like 1,000, that should be okay in terms of doing that. I wonder if I would put the other answer, if it would do it okay too. Okay, so this one on the left is negative. I'm going to go back to the between. A -1.57, and to the right is 2.57. This time it's not like balanced out, but that's okay. You could still do the area to the left plus the area to the right, or just do 100% subtract 94%. So it's about 6% that's not being shaded. So forth. The other one is just the same. So go ahead and complete it. Question number 8. Find the z-score such that to the area under the standard normal curve is 0.52. So the z-score is find the number of standard deviations. So that's a vocabulary word that maybe you want to write the definition for if you're not sure. The z-score is that x, which represents the number of standard deviations that you're away from the center. So like 0, 1, 2, 3, -1, -2, -3. These are the z-scores. These are the standard deviations away from the center. You want that x so that it takes up the area to the left of 0.52. So we're going to go back to standard. And this one is left. So we want the left-hand side shaded. But this time you have to be careful because this time they're giving us the space that it's taken up. So 52% is being shaded. So you want to put it over here on the right-hand side. So now they're shading, at 0, it'd be exactly 50% to the left, right? It's 52%. It's going to push it slightly to the right. So 52% of this entire curve is being shaded. Where is it? How many standard deviations is that from the center? Like really close to 0, right? Like 0.05 standard deviations, very tiny, 2 decimal places. So just be careful because sometimes they're saying how many standard deviations are you away with this area, or sometimes they're saying if I land here in terms of one standard deviation away from the center, how much area is that, which ends up being the probability. Okay, question 9. Another, find the z-score so that the area is to the right. So just you have to pay attention whether you're shading to the left or to the right. So this one's to the right. And again, they're telling us the area, which is 26% now. And if you're on the right side, this x value should be positive, right? If you're on the left side, then this x value should be negative. Because if you're to the right of 0, you have positive standard deviations. If you're to the left of 0, you should have negative standard deviations, right? So 2 decimal places. So somewhere between 0 and 1 standard deviation. Find the z-scores that separate the middle. So that's a between. And another thing you have to be careful here is that it's given to us as a percent. So when you put it on the normal calculator, you have to be careful and always put it as a probability, which is how we do it mathematically. Percent is just for the public. So if you want to capture 93% of the data, that's almost 95%. So notice how it's close to 2 and negative 2, but you're a little bit below. So it's actually at negative 1.8 and positive 1.8. Separate it by commas. Also put it in order from smallest to largest, because sometimes they mark it wrong. 2 decimal places, 2 numbers behind the decimal. So somewhere between negative 1.8 and positive 1.8 standard deviations, almost between 2. We have a mean of 50 for this normal distribution. Okay, they all show a mean of 50. And it deviates by 9. Compute the probability of being less than 47. So let's say the average age that somebody starts thinking about retirement is 50 years, give or take 9. What's the probability if I randomly choose a person that they thought about retirement younger than 47? What are the odds of that happening if this was the results of the survey that I collected, that the average age turned out to be 50 when I asked a bunch of people this question of all ages, give or take 9 years. So typical was between 41 and 59 if I add and subtract 9. So I can kind of get an idea of what the typical age range is. So which one is correct? So first of all, it has to be, if I randomly choose a person, it's below 47. So all of 47 is below to the left. So less than means to the left side, pointing to, see how this arrow is pointing to the left and this is shading to the left? It's the only one that's shading everything to the left of 47. So let's check that. And now find it. Okay, so now there's a couple of ways you can do this, but the easiest way to do is just go directly to the information giving us instead of standardizing it all. It's a lot more work. So the center is 50, give or take 9 years. So this is 50 years. This is 9 years. First of all, I have to put it also back in standard. And then to the left, this arrow should be matching what your problem is here. And they gave us the X this time. So that's 47. So this is 50 years, 9 years. What is the probability that it's less than 47 years? So all these units should be the same. Years, years, years. The only one that's not years is this one, because this one's the actual area that the curve takes, or the probability of that happening. 4 decimal places. There's 2 interpretations of this. One is that if I randomly choose one person, if I change this to a percent, that's almost like 37%. If I randomly select a person, there's a 37% chance that they would have thought about retirement when they were 47 years old or younger. Or the second interpretation you think of it as a population. So 37% of all people start thinking about retirement at 47 or younger. So you can interpret it as an individual or as a group. Okay, question 12. Here's another between. So let me do, oh no, just look at the tick marks showed up. So there's the one that I was talking about, 68, 95, 99.7. So let's go to a between. Okay, so here is 50 is the center, now 7. So maybe we can even do the phone bill problem. The average phone bill is 50, give or take $7 for an individual, maybe a senior quote for somebody who's an older or lower income. So that would be between $43 and $57 would be a typical bill for this type of person. Compute the odds that if I randomly select one individual, that their bill is between $34 and $66. What are the odds, or what percent of all bills are between $34 and $66? So the mean is 50. My standard deviation is 7. You put your own numbers there. And then I'm going to say 34, 66. So $50, $7, $34, $66. They're all the same units. This is the only one that's not in dollars, which is almost all, 98% of all bills will be between 34 and 66. But in terms of the picture, this one it's not a between, it's below. This one would be what percent of the population has a bill below $34 or over 66. And this one's just what percent of the population is below $66 because everything to the left is being shaded. Just to compare what all the 3 interpretations would be. And then about 37% would be between here and here of all. Now it's not drawn to scale, so just it kind of looks a little bit bigger here. If I did want to change it to the tick marks, then it would show me like 1, 2, 3 standard deviations. So somebody who's at $57 bill is 1 standard deviation above the mean, and somebody who's $36 who has a $36 bill is 2 standard deviations away from the mean. So when we change these to 0, 1, 2, and 3, it just tells you in terms of standard deviations, if you're unusual or not, if you're typical. Usually 1 standard deviation is typical. Above 2 is unusual, below 2 is unusual. By the time you get to 3, that's like extremely unusual, super unusual. But 2 is already unusual, which is kind of interesting if you think about it. Only 2 counts takes you to already be an unusual number. So like if the one I was talking about heights, where if you're 5'9" in the United States, and then this is 6 feet and this is 6'3". So anybody who's taller than 6'3" is already unusual for an American height in males. And if I add another 3, that would be 6'6". So 6'6" would be extremely unusual. I forgot to put my correct answer here, sorry. A little bit more challenging. A number of chocolate chips in a bags of Chips Ahoy 18-ounce bag is approximately normally distributed. Well, it better be, because they have to have, like those quality control machines, so that everybody, when you buy a bag of Chip Ahoys, you get the same amount of chips like any other bag would have. Okay, so it has a mean of about 1,662 chips, give or take about 118 chips, according to some study. Determine the 27th percentile for the number of chocolate chips. Okay, I already have my diagram here. So let's see. The average number of chocolate chips for my example is 1,262, give or take 118 chips. Let me go put in the standard one. The 27th percentile is I'm going to do the tick marks here so that the center, so that when I press the tick marks, it just standardizes everything. So it makes it like 1, 2, 3, and -1, -2, -3. So we can see what's unusual. So if you got more than 1638 or less than 886 chocolate chips in your bag, you counted them, that would be unusual and rare. Now that happens a lot, then we need to bring it up to the company's attention, right? Now, when they say the 27th percentile, think of this over here as like 0%, 10%, 20. Here's 50%, 60, 70, 80. And then when you get to the end, it's 100 percentile. So when you want to do the 27th percentile here, it's 0.27. Remember, change it to a decimal. You want to shade to the left to get that count. Otherwise, it's going to show the 27th will be over here. So, which is if you do greater than. Oh, I don't know if it would make a difference. Let me see. Oh, well, it just changes the, well, let me change that one. If I did the 27th here. Oops. Yeah, see how it's doing the 27th over here? That's more than 50% technically, right? So make sure it's to the left so that you're on the right side, on the, so these will always be left-hand side if you want the 27th percentile. And then round to the nearest whole number. So that's before the decimal place. Again, always look at the next digit to see if you're going to keep that number or bump it up. In my case, I have to round up. Let me see, 27. Let me check my work. Okay, so I did a typo here. A lot of places to make mistakes. That could be frustrating because sometimes you can't see where you make your mistakes. So sometimes it's just do a new problem and then maybe you can catch a mistake that way. Okay, so let me go ahead and put the new numbers in again. So this time it was 89.6. So that 89 had to be bumped up by one, or 1189 I had to add one. So that's 1190. Determine the number of chocolate chips bags that make up the middle 97% of all bags. So that's between middle. And here we're going to put 0.97. Let me do the tick marks again. I just like visually seeing my 3 standard deviations there. And round to the nearest whole number. So 97% of all bags will have between 1,006 and 1,518 chocolate chips if this company is doing its job. Always do smallest to largest. That's what ascending order means. Because if you just put it in any order, it's going to mark it wrong if you put the smaller number first. It's just the way that this is programmed. For part C, excuse me, you have to remember what this interquartile range is, which we abbreviated it as IQR. And that's Q3 subtract Q1. So the third quartile subtract the first quartile. So I have to find what the third quartile is, and then what the first quartile is. So let's do back to standard. Okay, I was just pause the video for a second here. All right, I was just going to see if there was a quicker way to do it. Okay, so when we usually use this in a box plot, and the QR captures the middle 50% of the data. So you could do it separately, like find the 25th percentile, find the 75th percentile, those two numbers and subtract it. But I think we can also do it if we do the between. And then put the 50% here. Let me, I'm not typing that correctly. If I want to capture the middle 50%, I could do the between, compute. And so that's between these two. So that's my Q3 is 1341 I guess I'm going to do it to the tenths. Let's say 6, and then I'm going to subtract 1182.4. Let's see what I get when I do that. 1341.6, subtract 1182.4, and get 159.2. Now, if I had rounded it first, then I would get 1342, because that 0.6 would bump up that one to a 2. And then if I subtract 1182, that 4, that 2 stays because that's a 4, equals, I would get 160. So I think if you put 160, it would still be okay. I think there's a little bit of wiggle room for that. I mean, that's the fastest way to do it. There's other ways to do this problem as well. A study found that the mean number of time cars spent in drive-throughs of a certain fast food restaurant was 143.2 seconds. And so, meaning drive-through times are normally distributed with a standard deviation of 25 seconds, complete parts below. So let me put that here first. So for my problem, the average time spent is 143.2 seconds, give or take 25 seconds. It's either 60 seconds in a minute. So for my problem, 120 seconds would be 2 minutes. So maybe between 2 minutes and 3 minutes for this particular fast food place. And yours might be a little bit different. Let me go back to standard. Okay. Tick marks. Sometimes it doesn't let me backspace this because I have 143 minutes, seconds, and then 1,118 seconds. That's kind of out of range. So that's why it didn't let me do that. Okay, so what is the probability as a decimal that a randomly selected car is less than 102? So less than is pointing to the left, 102 seconds. So 143 seconds is the mean, give or take 25 seconds. And we want to know what are the odds that if you randomly select a car that they waited less than 102 seconds. So that's why I like seeing the tick marks. So that's not unusual. It's low, it's below the average, but not unusually low. So you shouldn't be surprised to wait 102 seconds. I would be surprised if I waited less than 93 seconds, like a minute and a half, or above 193 seconds. So 4 decimal places. So the odds of that happening is about 5%. Or like 5% of all cars will wait less than 102 seconds under these conditions, which means that out of every 100 cars, 5 cars that go through this fast food waited less than 102 seconds. Okay, what's the probability that they'll spend more than 188 seconds? Like, we're okay if we're over here. We're not okay if we're over here, right? We don't want to wait too long. We won't complain if we wait less. If this is unusually fast, we're not going to complain to the manager, but if it's unusually slow, we will, right? Okay, so then more than is to the right. 188. I don't know why this is doing this. So here we see what percent of the population will wait more than 188 seconds, which is, slightly higher than 3 minutes. So about 4%. So 4 out of every 100 cars. And then checking the rounding. And then now we say between. So let's hit the between here, 2 and 3 minutes. 143 seconds, 25 seconds. And then you can't put 2 and 3 here because now it's, what is the odds that you're going to wait between 2 and 3 seconds? Probably 0. It's 2.1 times 10 to the negative ninth power, a very tiny, tiny number. That doesn't make sense, right? Why? Because this was seconds, that was seconds, and then they give you the units and minutes. So you have to be careful when everything doesn't match. So 2 minutes is 2 times 60, 120 seconds. 3 minutes is 3 times 60, 180 seconds. So just multiply the minutes by 60, and you can convert it to seconds. So the percent of cars that will wait between 2 and 3 minutes or between 120 and 180 seconds is about 75% for my problem. Or the proportion is 0.75 if you're talking about it in terms of a proportion. Been having to round up lately a lot. Okay, so now would it be unusual to wait for more than 103 minutes, this 180, which is here? So let's see. Just by looking at it, it's 1, 2. It's unusual if you're beyond 193, according to mine. Yours might be different. And I'm definitely not above 193, so it's not unusual. Now, so there's 2 ways to look at something's unusual. If you're more than 2 standard deviations, if it's perfectly normal, which usually in cases it's not perfectly normal, or if this percent is, remember, between 2 standard deviations, it's 95% of the population. So only 5% of the population is unusual. 2.5% over here and 2.5% over here. But usually we check with 5% or 0.05. If the area that it's taking up is less than that, then we do say it's unusual. Okay, so let's see what the actual percentage is. I already know it's not unusual because the area is probably more than 5% and because we weren't more than 2 standard deviations. All right, so more than 3. So let's go back to standard. And now more than 3 would be more than 60 times 3. But if it said more than 4, then you would do 4 times 60. So let me first see what the odds of that are. 7%. See where I landed? Somewhere between 168, 180, 93 is 180. And that's not more than 2 standard deviations. And it's 7%. That's low. The odds of that happening, 7 out of every 100 cars is low, but not low enough to say, oh, wow, I would be surprised by that. That's unusual. It'd have to be less than 5 cars per every 100 or less than 5%. Okay, so the probability is about 7% for mine, or whatever yours is. If yours is less than 5% or more than 2 standard deviations away, then you are going to say it is unusual. So would not in my case, but it could be that in yours it is. Since my answer was greater than 0.05. But if your answer is less than 5%, then yeah, that would be an unusual event. We're almost there. This was a long one. Okay, let me close this because we're going to have a new, let me open this in StatCrunch and make sure to share that with you. Suppose a sample of O-rings, think of them like a little washers, was obtained, and the wall thickness, if you don't know what a washer is just like a little circle that goes in nuts and bolts, little metal circular piece. And the wall thickness, or the thickness of this little metal ring, was recorded, and use a normality plot to assess whether the sample could have come from a population that's normally distributed. Okay, usually you want to have a sample size of for quantitative data, numerical data, you want to have at least 30 in your sample size. That seems to be the magic number. So when you're less than 30, it doesn't mean you can't do the analysis. It just means that the conditions weren't met. So you might have to check another condition. And if this is like normally distributed, roughly normally distributed, like you don't have any outliers or any one answer that was really far away from the other, then you're probably still okay to do the analysis. So the tricky part here that it's called a normal probability plot here, but on StatCrunch it's called something else. It's called a QQ plot. So you go to graph and do QQ plot. You select your variable, and you want to select the correlation statistic. Sometimes you have to click this one on certain problems. So let's compute. So it puts the Z value here, and it puts like the distance here. We usually like the normal values to be on the other one. Do you have to do that? We're really looking at this correlation coefficient. We call it the R value that we talked about in chapter 4, but it's being used slightly different here. Just out of curiosity, if I switch it, like I put the Z values here and the values here, it's still the same thing, so it doesn't matter. But be careful when they ask you these type of questions in this chapter. Sometimes this is flipped where they give you the graph, so you might have to do the options edit and flip it as well. Okay, so is that a strong, like this kind of changes like how far you are from the, if it was normal, you should land here. This is how you're a little bit not normal, but like if there was a point like way over here, then you would know definitely that that's an outlier. So at what point do you decide like this one who's like this distance away from which, if it were to be normal, is unusual? And it's a nice way to measure that. So this is a pretty high correlation, but it does depend on how many values you have here. So what we do is we compare it to a table. So let's see, click a table for the critical values. Here it is. Sometimes it's not available, so I put it on the home page in Canvas under the some useful handouts on the first module. So you look up your sample size, in our case is 16. So your critical value has to exceed 0.941 in order to say that this is normal enough. And ours is 960. Well, my value is 969, which is higher than this cutoff. So if mine had been weaker than this number, then I can't do the study. I have to go back and maybe measure some more O-rings. But since my the strength of my association here is higher than the cutoff, this critical value, then we're okay. I don't know if they're going to ask for that, so let me write it down here. Close it. So using this correlation coefficient of this normality plot, and that's why we did it in our project. We made one of these to see if in case we didn't have our sample size for our project was less than 30, if it satisfies this little check, then we can still go ahead and use those numbers in our analysis and still be accurate. But if it's not, we can just put that in our conclusion saying, okay, these results might not be accurate because we didn't meet the conditions. Okay, so our conditions was met. So I have 2 yeses, so I'm going to choose between yes. The correlation between the expected z-scores and the observed data, which is for me 969, exceeds the critical value. Therefore, it's not reasonable to conclude. And over here it says it is reasonable to conclude that it came from something that's normal. Well, since ours is stronger than this one, then yeah, this one is reasonable to conclude that it is pretty normal. In fact, I can even make a histogram to kind of see that, I don't know if you consider that normal, but maybe if I make these units a little bit different, or if that doesn't really show me, maybe a box plot might show me if it's normal. Because that one was sometimes we can't see that normality. Sometimes it's easier seen in a box plot. It's a little bit right skewed because this distance here is slightly to the right, but yeah, it looks pretty symmetric, not too bad. So again, it's not perfectly symmetric. Is it symmetric enough? That's what we're doing here. Is it symmetric enough? Yes, because our value exceeded this one, and I don't see any outliers here. So sometimes we look at the box plot to see if there's any outliers. So okay, so yeah, B, yes. Our correlation coefficient is higher than the cutoff, that critical value that determines if we can do this. Oh, and that was it. Sometimes they'll follow it up with the box plot. That's why I left it up here. So maybe it's the next question, or maybe on your homework question. So here's another one. A random sample of 16 undergraduate students. So let me open this in a new StatCrunch. So like on a test, I would recommend that you open a new page and close the previous one, because sometimes you might be looking at the wrong data if you keep a bunch of tabs open. So that's what I would recommend. So I've been trying to close them and just open a new one when it's something new that I'm going to be using. So a sample of 16 undergrad students received student loans was obtained. So they recorded all the student loans. Use a normal probability plot. And they don't tell us if this was over the entire years of study or if it's just 1 year. Okay, so because again, we don't have a sample size of 30, can we still do this? Well, as long as an alternative condition is met that this is roughly normal to begin with. Again, I can look at the box plot and make sure there's no outliers here. I can look at the QQ plot, make sure that condition is met. So QQ plot, correlation coefficient. I'm going to put the normal quartiles on the x-axis as well. I just like to see the z values here and the loan amount here. So yeah, everything looks pretty lined up. It's 0.98. So R equals 0.98. And I already forgot what the value was for 16, the critical value. So critical value equals 0.941. This one here, sometimes there's optional tables, and just be careful. This is for schools that don't have StatCrunch. They have to look up everything manually in tables. That area, where we get it from the normal curve on StatCrunch. So that's why we didn't use that. So just because it's there doesn't mean that you're supposed to use it. So just watch out for that. Okay, my 0.98, I forgot my decimal point there, is higher again than this cutoff of 941. So yeah, it's normal enough. It might not be perfectly normal, but normal enough where I can just still use the normal curve to find probabilities. So again, from yes, therefore it is reasonable. So yeah, because it exceeds, it's reasonable to continue with our study. So this time my R value was 0.98. This time the cutoff is still the same, 0.941. You can put a 0 in front. Sometimes I do. Sometimes I just skip that. That's okay. And maybe on the homework they would look for a normal work on our project. We'd probably look at the box plot to make sure there's no outliers. And so it's like two conditions. If you don't meet the size condition of 30, you want to do this little check, and you want to make sure your box plot is roughly normal and that there's no outliers. And if there is, you're still going to do the project, but you just kind of put that in your conclusion that perhaps your all the analysis that you did might not be accurate. Okay, that looks like that was the last problem.